Hi, my name is Dylan Shim, and this is my presentation for the COT 6427 course, Secret Sharing course. So my topic is Shamir's secret sharing scheme used for sealed bid auctions. So in this presentation, I will be going over the problem motivation, the background information about secret sharing, Shamir's secret sharing scheme, sealed bid auctions, and also my implementation. So first of all, traditional auctions generally display all of the placed bids where bids are usually placed in real time. And this can lead to some security issues as every bid is known by the auctioneer and the bidders. So this can be a problem, especially since the bids on items of high value are publicly known, and also bidders may illegally collaborate, which can result in collusion. And when collusion occurs, this may consist of the bidders secretly collaborating in ways such as not bidding to reduce bidding competition or by withdrawing their bids in order to win an auction at a lower price, which is illegal. Additionally, in traditional auctions, bidders can adjust their bids based on the value of other bids, and this can result in placing bids lower than what an item may actually be worth, which negatively impacts the seller. So by introducing privacy within an auction, by keeping all the bids hidden, then the bidders will not be able to gain any advantage by learning other bids early, which this is able to promote fairness within the auction. Also, this prevents illegal collaborations among bidders, which is important for high value items. In addition, it decreases the chances of bidders placing bids based on their emotions or feelings. And also, sellers may benefit by potentially gaining higher bids since the bidders since bidders may place their most competitive bid since other bids are not known, and also since they only get one chance to place a bid. So the contributions of this project consist of implementing Shamir's secret sharing scheme, and in addition, a sealed bid auction was generated along with this secret sharing scheme to keep the bids hidden, where this implementation demonstrates how secret sharing is applied to all of the bids placed within the auction, and also how the bids are reconstructed. So secret sharing involves the process of splitting confidential data, which this confidential data is known as the secret, into multiple shares. And these shares are then distributed among multiple players or shareholders, where only a certain number of players can combine their shares to reconstruct the secret value. And secret sharing allows for private data to be shared securely without the actual data being exposed. So this is beneficial as it prevents a single corrupted individual from being able to access, steal, or manipulate the sensitive data. So in Shamir's secret sharing scheme, there is a threshold value, and this threshold value represents the minimum number of shares that are needed to be able to reconstruct the secret value. So if the number of shares that you have is greater than or equal to the threshold value, then the secret can be reconstructed, where on the other hand, if the number of shares is less than the threshold value, then the secret cannot be recovered. And this prevents any single point of failure while also making sure that the system stays robust, since the secret can still be recovered even if some of the shares are lost. And as long as you have T number of shares, then you can still recover the secret. So as you can see in the example, if there are 7 shareholders, meaning that a secret value is split into 7 shares, and the threshold value is set at 3, then you would need at least any 3 of the 7 shares to be able to reconstruct the secret. So in Shamir's secret sharing scheme, it requires the use of polynomials in order to hide the secret value and also generate shares of the secret. And to create a random polynomial, it must be of degree t minus 1, and the coefficients of the polynomial are randomized. Additionally, a secret value is stored as the polynomial's constant term, and then evaluating the polynomial on each shareholder's index, which is from 1 to n, then this results in multiple shares being produced. Each share then represents a point on the polynomial. So the polynomial example shown at the bottom, which is represented as f of x, is represents the format for the random polynomial to be created. And as you can see, the secret value is supposed to be the constant term of the polynomial, and the polynomial's degree is of t minus 1. So the secret is found by putting together any t shares to reconstruct the polynomial, and then evaluating the polynomial at 0. So as I mentioned below, t number of shares will not provide any information about the secret, showing how this secret sharing scheme is secure. So to reconstruct the secret, and more specifically, we use Lagrange interpolation. And the formula for Lagrange interpolation is shown at the top, where when using t shares with this formula, the polynomial can be reconstructed, and since the secret value is found when the polynomial is evaluated at 0, then we set x equal to 0 and then use the Lagrange interpolation formula, which is shown at the bottom, where, as I said, the value of x is set to 0. So moving on, a sealed bid auction is an auction where all placed bids are kept private, which this prevents any bidders from knowing the bids of others. And the main goal of a sealed bid auction, when in terms of the bidders, is for the bidders to essentially place the highest bid in order to win the auction. So the main goal of sealed bid auctions overall is that they is for none of the bids to be revealed in order to promote fairness, as each bidder is given an opportunity to submit their best offer up front rather than seeing other players' bids, and this also promotes security. So when a secret sharing scheme is applied within a sealed bid auction, then all the bids within the auction are converted into shares. And this prevents the bidders from seeing any full bid, and also the bids are able to stay hidden until the end in order to find the winning bid. So this is a system workflow of Shamir's secret sharing scheme for a sealed bid auction. So to go over this, as we can see from the top left box, we have n equals 5 players, and then we also have t equals 3, which t is the threshold. So as we can see, we have bids for each of the five bidders, and then in order to implement Shamir's secret sharing scheme, we would then create a random polynomial which is of degree t minus 1, which in this case would be 2, where we also have random coefficients, which are the a values that which the random coefficients allow for randomness of the polynomial. And then, as we can also see within the polynomials, the their secret or original bid value is hidden in the polynomial as the constant value. And so once the polynomials are created, then we can generate shares of each bid, where this would just be done by evaluating the polynomials at the different indexes of each shareholder. And once we obtain the shares of each bid, then each share is then distributed to among the shareholders. So each shareholder will obtain their corresponding share. So after each shareholder has the shares of each bid, then a trusted auctioneer will then collect 3 shares of each bid in order to be able to reconstruct the secret. And for this, the trusted auctioneer would have to apply Lagrange interpolation to reconstruct the secret. And again, in this case, you would be needing 3 shares to reconstruct the secret because the threshold value is 3. So anything below 3, any shares put together through Lagrange interpolation below 3 would not be able to reconstruct the secret. And once the trusted auctioneer reconstructs all of the bids, then they can then identify the highest bid and then reveal the winner. And one thing to note is that the once the bids are reconstructed, then these bids are only visible to the trusted auctioneer. So to implement Shamir's secret sharing scheme for a sealed bid auction, I used C++, and in order to accommodate for a large integer value, the Boost multi-precision library was used. The outline of my code follows the structure shown on the right side, where first the threshold and the number of shareholders is initially set, and then after this we generate a large prime value of 128 bits, and then the bidder information is inputted, where the user will be prompted to input the names of the bidders and also their bid values. After this, the random polynomials are created per bid, and then shares of each bid are obtained through polynomial evaluation, where these shares are then distributed among the multiple different shareholders, and then after that, reconstruction of the bids through T shares occurs, where yeah, as I just said, you need T shares to be able to reconstruct the bids. And finally, the bids are compared, where the highest bid is then revealed. So within my implementation, I have 2 structures, where the first one represents 1 point on the secret polynomial, so it has x and y, and the second structure is for storing the bidder's information, such as their name, their bid, and the shares of their bid. The functions within my code that are utilized to generate the large prime finite field value are shown here. When a random 128-bit integer was generated, then the Miller-Rabin primality test was implemented in order to ensure that it was prime. And if it was not a prime value, then a new random number of 128 bits was formulated until the value was prime. And the implementation followed the algorithm that's written out on the left side of the screen, as that represents the Miller-Rabin algorithm. And in addition, I also used Fermat's little theorem to be able to compute the modular inverse, which followed the formula on the right side. So within the implementation, there are multiple functions used for generating shares of each bid, where the function names are shown on this slide and towards the top. And so first, we have a function that's used to generate a random polynomial of degree t minus 1, which follows the format shown here in red. And then another function is used to evaluate the polynomial to generate shares which are distributed to multiple shareholders. So on the right shows an image of the function that's used to perform Lagrange interpolation, where as you can see, we first obtain the numerator portion, which is negative x sub j, and then the denominator portion, which is x sub I minus x sub j, where the product of the numerators and denominators is calculated within the inner loop, which matches the equation. Then Fermat's little theorem is used to find the inverse of the denominator so that it can be multiplied by the numerator, where this result is multiplied by y sub I. And then this process repeats as it follows the outer loop, where the sum is then calculated to obtain the secret value. So for the sealed bid auction process within my code, we initially set the threshold value and number of shareholders, and then the prime modulus value is generated. Next, bidder information is inputted, and the shares of each bid are then created with Shamir's scheme. Next, shares are distributed to the shareholders, and then T shares are collected to reconstruct the hidden bids, where finally the bids are compared and the winner is displayed. The bottom of this slide shows the function names that are related to the sealed bid auction within my code. When looking at our code's output, we can see that a very large prime integer is created as the p-value for the finite field as shown towards the top. And since the threshold is set to 4, we need at least 4 shares to recover the hidden bid values. Additionally, we initialize the number of shareholders as 7, and after this, the bidders' names and the bids are then submitted into the program. And moving on to the next slide, we can see that within these images of the outputs, that once the bids are submitted, the bids are completely hidden through Shamir's secret sharing, where only the shares of the secrets are known, and these shares are shown in the first two images for demonstration purposes, where in a real sealed bid auction, you would not be outputting these shares, because then it can lead to some players being able to reconstruct the secret potentially. And these shares are all distributed to multiple different shareholders. So during the reconstruction phase, the bids are successfully recovered using the minimum threshold value of 4 shares, in which the winner is correctly determined, and in this case, the bidder whose name is Doug is displayed as the winner since his bid was the highest at 94,200. So when using Shamir's secret sharing scheme for a sealed bid auction, as shown within this implementation, there are some limitations. The main limitation is that once the bids have been reconstructed in order to determine the winner, then all the bids are known, and some problems that may occur is if a corrupt auctioneer unfairly manipulates the bids or the winner, or if the auctioneer releases the bids publicly, which should not be done as the bids may be considered sensitive information, and if the seller unethically keeps track of the bids placed for personal gain. And for instance, if a seller knows how much bidders are willing to bid on a certain item, then if they sell a similar item in the future, they can unethically place bids on their item that are just below the maximum bid value that was previously placed on the similar item just to sell something for more money. And some other limitations are that is that the secret sharing scheme requires communication among players, which can take extra time if some participants are not available. And lastly, it's possible that players may come together and reconstruct the secret value if the number of corrupted players meets the threshold. So, overall, our implementation show that Chimera secret sharing scheme be can allow for secure data sharing and also be applied to a sealed bid auction. And for the future, I would integrate secure multi-party computation since this allows for various computations to be performed on the shares, and also it will allow for a complete secure overall program by using a secure multi-party computation for a sealed bid auction. Thank you.